So I'm Brad Malin. It's really an honor to be here. I really appreciate the invitation. It's been great listening to what the programs have been up to over the last year. You have really jumped forward by leaps and bounds. So hopefully what I can do today is give you a little bit of intuition into some of the things that we've been thinking about and see if it's useful for you at all. So I'm going to talk a little bit about machine learning. But before I get to there, I need to give you a little bit of background on why we did it and why I work in this space. So some of you who have heard me before are familiar with this program that we started in the United States that's known as the All of Us program. If you're not familiar with it, this is a program that started to create a cohort of 1 million volunteers giving us their medical records, their biospecimens, survey information, as well as mobile fitness tracking information. And so the expectation was that this would be used for the betterment of health research. This is an extremely large initiative. It started under an executive order that President Obama gave right before he left office. And so this program starts, and then everybody said, well, what could possibly go wrong? And the number one thing that was on people's minds was privacy. And you probably have no idea who this guy is. And most people in the United States have no idea who this guy is. But this is the guy that really led to a lot of the freak-out moments associated with identifiability with medical records data. So this guy is William Weld. He was the governor of the state of Massachusetts, and he was receiving an honorary doctorate on stage. This was like 25 years ago. He's receiving this doctorate, and he collapsed while on stage, and nobody really knew what happened to him. Now, what happened, though, was that at the same time, in the United States, a lot of the states started collecting hospital discharge data, and they were making it available for performing comparative effectiveness analysis across different regions and with respect to how particular clinical phenomena were treated at various facilities. And so this was the type of information that was being made available at the time that the governor had this clinical problem. And so what was known, though, was that he was going to show up in this data. Now, what they didn't expect was that he also showed up in publicly available data that we had in the United States that included his personal identifiers, his name, where he lived, and this was because in the U.S. we have a lot of public registry data, and so this was voter registration information. We don't publicly disclose how somebody votes, but we do indicate if they voted and when they voted. And so this was available for a relatively nominal fee of $20. And so these two pieces of information were crossed. And when they did, they found out that at the time he was the only person who lived in his geographic area of residence that had his date of birth and was his gender and was admitted to Massachusetts General Hospital at that time. Okay, it was a very, very simple integration. And it freaked people out, right? As you can imagine, right? So this was the re-identification attack that kind of led to all of these really challenging concerns. So when we went about to building the All of Us environment for how we were going to share data, this was really in the front of our minds because the last thing that we wanted was to end up on the front page of the New York Times in a bad way, right? So we created several different tiers of access. And one of them is what we call the public tier. And this is a tier that can be accessed by anybody without logging in, anybody in the world. And it provides summary statistics about what we've collected. And so if you're interested, you can go to this website. Just go to databrowser.researchallofus.org. And you can start browsing yourself. You could do that right now if you want to. Though I found that the network connection in here is a little weak. So what you can see is that we provide summary information. This is just with respect to clinical conditions. And so we round the numbers. We round them to multiples of 20 so that you can't triangulate against a specific individual. So that's like a very high level perspective. That's stage one of what we created. And then we started to move towards providing access to individual level records. And the way that we did this was that we moved all the data out into the cloud. Right now it's all hosted out on Google Cloud. And on top of GCP, we are invoking what's called the Terra system, which is a workflow management and workspace management environment, on top of which you can build things like Jupyter Notebooks. A lot of people familiar with Jupyter Notebooks? Becoming more familiar with Jupyter Notebooks? That's kind of becoming the de facto standard for data science investigations. But within it, we created these two tiers. And one is what we refer to as the controlled tier. And this is an environment that is made available to to trusted investigators. And this is because we have whole genome sequencing data in there on these individuals. Now, I'm not going to talk a lot about what makes for a trusted investigator today. I think that we're going to hear more about that in the next talk. I'm just going to say that imagine that we have an ability to say you are a bona fide researcher and you're allowed to come in. Okay? So public, controlled. We then built something in between. And what was in between is what we referred to as a registered environment. And this is available to anybody who comes from an institution that enters into an agreement with us that says, I take responsibility for the actions of who comes in there. And so then the user will then also have to enter into a use agreement with us. They actually have to pass an exam, an ethics-related exam of why they're going to be in there and what they're going to do. And this is an environment that we've assessed to show that the risk of re-identification or the freak-out moment with the governor is very unlikely to happen. So I get lots of questions about, so what did you do to the data? And so this is just a quick intuition, a quick summary of just to show you that when we talk about privacy, we make changes to the data. And so some of the things that we did was that we shifted the dates of events for the individuals, and it was done randomly on a per subject basis. We generalized certain facets about them. So their occupation was not explicitly disclosed. For certain types of people, their race or their ethnicity was obscured because we had some small populations. And then there were certain things that we just removed from the registered tier, but we make available in the controlled tier. Things like the exact cause of death, or whether or not they were an active member of the military. So we made some changes. And so this is why, you know, as a person who works on privacy, I look at this and we're using this principle of de-identification, which you know, you might have heard of. In the EU, it tends to get referred to as anonymization in general. And this is it's a principle that I don't find to be an ideal. And one of the reasons is that, you know, the smaller your population, the more likely that there are going to be facts that are going to be changed in some way, right? So it might be that they are the only black person living in the middle of Alaska, right, in your cohort. And so it's going to be difficult to retain information on an individual like that. And this can have major implications with respect to bias in your data set, as well as the generalizability of any machine learning algorithm that you learn on top of the data. Okay? So the way I like to explain this is we tend to think of this as a data privacy and data utility trade-off. And the trade-off tends to look like this. It's not exactly a linear line, but go with me. It's an illustration. All right? The issue is that you get different lines for different populations. Okay, so a majority population will look something like this. But when you start talking about a minority population, they start with less utility because they don't have as many of them in the data. And then the trade-off ends up being more steep. And in fact, you can never achieve as much privacy for them as you might even be able to achieve for another population. And then you can shift to like a super minority population, which we run into challenges about in the US because we have relatively small populations of Native American groups. And so it's this challenge that it's what we like to refer to as it's the no free lunch problem with privacy. The reason this becomes an even bigger problem is that what we try to do is instill an equal level of privacy for everybody. And when you do that, then what ends up happening is that you end up setting different operating points for utility for all of these groups. Okay, so if you choose a single privacy measure, a single privacy threshold, you can see here that these groups, they get different overall benefit at the end of the day, right? That's a problem. So we're sitting here and we're going, well, what if there's an alternative? And one of the ways that you could think about these alternatives is let's try to think of what we're trying to accomplish. All right, we want to build an algorithm, and we want to minimize the bias that we're going to learn in that algorithm. Now that is, we're arguing that is an artifact of insufficient representation in the data. So what if you could make records for them? Okay, now this is a wacky idea when you think about it. It's like, what if you could just totally invent a record for people, right? And so it's not really that wacky when you think about it. So we're going to call this the synthetic data problem, all right? And so the question then becomes, how do you go about making records for people? And so one of the simplest ways is you could do what you call perturbation, all right? So perturbation would say, imagine you have a bunch of records that you begin with, right? And they've got different features associated with them. So one person might be white, one person might be black, and so there's differences between them. And so you're going to induce, let's just say, a perturbation strategy. So you're going to make changes to the data. You might fuzz the data so that you get something that looks like the original records. Okay, so when you fuzz it, you get something that looks a little bit like, a little different here, a little different there. But in this type of a perturbation strategy, and I'll get technical for a second, for those of you that are familiar with principles like differential privacy or k-anonymization, these are what these techniques try to do, where they're going to try and make some new representation of the data. Okay, and you could say here's a new record. So this is like the old school approach. I come from a machine learning community, and so I was like, well, why do we have to do it this way? And so what we did more recently is we started thinking about generative models. And so we learn a model off the data, and instead of trying to make little perturbations to existing records, we're just going to create completely new records off the model. All right, so I might get records that look relatively similar to the original records, but then I might end up getting records that look completely different, things that I've never seen before, almost hypothesis generation concept. Now, this notion of synthetic data, while I'm trying to make it seem, somewhat new, it's not really new when you think about it. So this notion of creating things that we haven't seen before, this is a concept that DeepMind and people at Google were thinking about at least for the last decade. And so if anybody's familiar with Ian Goodfellow's work, Ian's been showing how to do this with images like faces for the last 10 years or so. Now, you might not think of this as synthetic data generation. How many people have heard of deep fakes? Deep fakes? Anybody? No? Come on, more of you must be thinking of deep fakes. All right, deep fakes are synthetic data. They are literally synthetic data. Okay, so it can be used in a negative connotation, but it could also be used in a positive connotation. Now, synthetic data, it's actually even older than you might be thinking about, because if you're thinking of like image processing, that's like really becomes sophisticated in the machine learning community in like around 2010, 2012. But the notion of synthetic data in the healthcare domain, it actually goes back over 25 years. And so some of the first work I have to attribute to Jerry Ryder, who's a professor at Duke. And Jerry was talking about how to create synthetic data in very simple forms. He was looking at multidimensional contingency tables. So you have like very structured data, counts of information. But it's the equivalent of synthetically generating a record, because you can say, I have a table that says how many men by how many geographic region by how many age, okay? And so he starts this work, and then he says, well, there's probably some concerns associated with this data, and I'll get to what those are in a moment. I should be clear, that first paper he wrote back in 2002. When he started talking about some of the privacy principles, this came out in 2009, and then Jerry did something that was what got us thinking about this, which is he said, so what happens if you take synthetic data and mix it in with real data so that you create partially synthetic data? And that's kind of what we want to do. So we're not doing anything new so much in that concept, but the way they used to do simulation was not machine learning driven. So we started to take some of the new machine learning techniques, like generative adversarial networks, which you may or may not be familiar with. If you're not, I'm going to walk you through it, right? Because I think it gives you some intuition into what the power of machine learning can be here. So the way a GAN works is that you'll take your real data, and then you'll learn a deep net representation for it. Okay, so pick a large artificial neural network, and you're going to use it to represent the data, just like you're going to do machine learning. And then off of that model that you learn, you do something a little different than what you would do. It's not for classification purposes. You take that model and you simulate new records off of that topology, and you'll generate what I call a fake record. And then you go to a second deep net. Okay, so this is where things get a little funky. So now I'm going to go back to the way that you'd use traditional machine learning, which is I'm going to build a classifier. And this classifier I'm going to use to tell the difference between real and fake, 1 and 0. Okay, tell me the difference between 1 and 0. Now the way I do so is that I'm going to pass it records, right? So I pass it a fake record, and I'm going to say, hey, could you tell me what that is? Now, if this discriminator can tell me that it's fake, I have a problem. And this is kind of where machine learning kind of gets flipped on its head. Because a traditional classifier, you want it to be able to tell you that something is from a certain class. But in this situation, we don't. We actually want the exact opposite. So if this discriminator is capable of telling me that something is fake when it really is fake, I want it to be able to go back and say, your network isn't the right thing. Go back and tune, do back propagation, fix the network. All right? So we're going to go tune, and then we're going to generate again. Now, in this situation, I'll show you we pass a real record. And it says, OK, I can tell it's a real record. Again, that's a problem. So we go back and we say, go fix the network. And so we're going to keep passing information along until it starts to be confused, right? But it must have a topological representation of the real data such that it should be good data, right? And by good, I mean there's going to be a reason why it's useful. All right, so you keep doing this tuning until it can't tell the difference. And that's when you stop. Okay, this was one of the breakthroughs that Ian Goodfellow had come up with. And so we hacked this. Now, this is where you got to take a step back and say, maybe you're saying this sounds really familiar. So how many people have used ChatGPT? You are using a GAN. So GANs, the whole premise of ChatGPT is that it does a little bit more than a GAN. It uses some reinforcement learning as well. But the way in which it is capable of creating a conversational representation that you interpret and looks like a human is talking with you is based on the concept of a GAN. It tries to say, is the computer talking to you or is the human talking to you? And that's how these GANs, how these conversational robots have gotten so good. So I'm just showing you an illustration here. I went to ChatGPT yesterday and said, could you generate a patient record for me? I said, give me a set of ICD codes, all right? And so you can see here it gave me a bunch of diagnosis and procedure codes. And so it was capable of doing so. Now, the question is it useful? That's a whole nother question that we're going to come back to, all right? All right, so this was a line of research that we started working on, I'd say back in 2016. And I have to give Jimeng Soon, a collaborator of mine at University of Illinois, a lot of credit for cluing me into this. And so we took a couple of data sets, one that's known as the MIMIC data set from Harvard. It's an ICU data set that's publicly available, and another private data set from Sutter Health out in California. And we did exactly what I just showed you. We trained the GAN to create records of demographics and diagnoses and procedures and medications, and then we tested how well, given some of the information, could I predict the presence or absence of another piece of information, like a diagnosis I haven't seen yet. And so what I'm showing you here, this is not my graph, this is on the bottom, this is how well something should be represented in the synthetic data, on the real data on the y-axis, and the synthetic data on the x. So perfect representation will be a 45-degree angle. This is what you end up getting if you use something like a variational autoencoder. Okay, that was kind of like the state of the art back about 10 years ago. And then when we did a GAN, we could see that we would have, it wasn't perfect representation, but it was pretty good. We were starting to feel good about this. All right, so we feel like we're on to something. And so then we recognize that we probably don't have the best way of doing simulation. And so why that was the case is that the old school technologies, and the one I just showed you, which we called MedGAN, it embedded an autoencoder in the middle of it, and it was using a distance function that wasn't so great. And then what we recognized, and it turned out that we recognized this at almost the exact same time as another group in Taiwan, and we ended up having almost competing papers, was that that distance function could be replaced with what's called the Earth mover's distance, or Wasserstein distance function. And it's a much more amenable towards these types of analyses because it's a more continuous representation of the system. The reason why that matters is that at the time, what we recognized was that the way everybody was evaluating their systems was that they cared about these first-order statistics, right? Could I predict something or could I not predict it? Now, I should be really clear here. What I'm showing here on the x-axis is the rate at which a diagnosis code shows up in the synthetic data, and in the y-axis, it's the rate at which it shows up in the real data, okay? So similar concept to what I showed you before, but you should see a 45-degree angle. And so what you can see here is all our original system, it looked good, and these were other systems that were coming out at the time. This was a new system that we had created. They look really similar in first-order statistics. When we went to second-order statistics, and we started looking at latent representations of the data, like you do a principal components analysis or an independent component analysis, here's the real system. This was our original GAN-based system. These were the other GAN systems that people were building at the time. And then this was what happened when you changed to a Wasserstein distance function. It was almost night and day. But at the time, everybody was looking at this and saying, these are all really good systems. And we said, no. You got to look deeper at the data. So that was one of the big advancements that I think we published about a year and a half ago. And then we started looking at generative models, and we probably noticed something that everybody now refers to as hallucinations, where we were generating records where we had women with prostate cancer. And we're like, that's not something that should happen a lot, right? And so we started working on techniques for doing probabilistic embedding of constraints into these systems. They're not perfect. You can still have problems, but you can embed constraints, which is really actually quite fascinating to us because it suggests to us, and we have a paper that's going to be coming out on this in a couple of weeks, that you can actually detect and mitigate hallucination in generative systems in a lot better way than what we're currently doing. And then we said we need to move from just doing a static profile of a combination of diagnoses and procedures to what those look like over time. That's a non-trivial problem. And what we ended up doing, and this is ugly, right? But what we ended up doing was we basically hooked a GAN up to a recurrent neural network. And when we did that, we were able to simulate the next visit for the patient. So given that they had a diagnosis or a medication at a previous visit, we could then say what's going to happen to them at their next visit, and then what happens to them at their next visit. All right. So this is an interesting idea, and then we found that it ran into some problems. It seemed to work, but one of the problems was that we noticed that unless you have feedback on how well that system is doing, it will tend to drift, and you will compound errors over time. And so we ended up generating a new technique called condition fuzzing and regularization to prevent this from happening. This is from a paper we published about a year ago now. Main story, I love this is my line is better than your line graph, only the baseline is actually my method, and the blue line is my method as well. What you're seeing here is like how well could we tell the real versus the fake data in the simulation. And this is what happens as you simulate over time. And we did this with two different data sets. We took one from Vanderbilt, and then we took another one from the All of Us research program. All right? And so what you can see is that this is the system that we originally developed, which just used a recurrent neural network. And then this is what happens when you put a feedback mechanism into the system. And so lower is better. All right? And that's really all that we're showing here, which is that drift happens, but it doesn't have to happen in a bad way. Okay, so while we're doing this, there was this really interesting concept that was introduced in the machine learning community called augmentation. And augmentation said, hey, if you create fake data and sprinkle it in with your real data, you can generate better machine learning algorithms. So we were originally doing this just for privacy purposes. But it turned out that it could be hacked to turn it into an improved classification environment. So these were two papers, two really great papers that came out in 2018, both of them on image processing. And what you can see in this one, which was looking at trying to predict whether or not you could detect a liver lesion, was that as they increased the system with the number of training samples, the classification performance got better, up to a point. And then they started introducing synthetic data in images, and you can see that they really put the system into turbocharge. All right, this was a similar paper that was looking at more generic predictions on time series. So these two papers came out at about the same time. The reason why this works is that if you imagine that this is your space of you've got two classes, okay, positive and negative, a traditional machine learning classifier would give you a margin that looks something like this, all right? But it's not perfect, right? And we also don't know exactly what's going on with this weird thing up here. And so what happens with synthetic data generation is that it tries to interpolate the space. Now, you need to have enough data to begin with, otherwise this thing is going to just give you random noise. But what it does is it's going to amplify things that have small representation to begin with. And so that margin is not really going to be where you end up. You're going to end up with a margin that looks like that, which is a much better representation for that system. So this is a really interesting phenomena because it suggests that synthetic data augmentation is not always going to make the system better. And we've actually had lots of cases where that is the situation. We just haven't been able to publish them because you can't publish negative findings easily. But it does suggest that there are going to be many situations in which this does work. So we've generated two synthetic data sets for the All of Us program that we're now in the midst of working on a public release for, one for breast cancer cohorts and another one for type 2 diabetes. And those you'll see later this year. Okay, so I'm just about at the end, and so a couple questions here. So, did generative AI just save the world? Again, right? Not quite. Right? So as I alluded to, hallucinations are real, right? The research is advancing on how to stop them, but it still has a long ways to go. Secondly, you need to validate the clinical face validity of these records. And what I showed you was predictive performance in a statistical sense. that's not the same as going to a doctor and saying, does this actually make sense to you? Because if they don't agree with it, you're going to have problems in terms of acceptance of what you've generated. Also, if you don't have enough data to begin with, as I alluded to, you're basically just going to end up generating noise, and the data is not going to be that useful. And then also, there's a limit to learning, right? So as the number of variables grows on you, the chance that your data is going to be useful is going to go down. And this was one of the major findings from our original paper on this, which showed that you probably don't want to learn a model for an entire population. You want to learn in a conditional manner for different populations and simulate new records accordingly. And then the last thing is that you have to be really careful from a privacy perspective. And so there's been various investigations to show that you can invert these systems in certain ways. So this is another one with visualization, where here's a visual representation of a face that was simulated, and here's the original training data. And you can see there's a lot of similarities there, right? That's the expectation. In fact, like, it's designed to do that, but you don't want that exactly to be the solution. So in the context of health data, you run into a couple problems. One is you can have mimicry, where if you don't have sufficient training data, you'll end up just mimicking the original records. This is an artifact of what's called mode collapse in the network. Secondly, you can have what's called membership inference, where in a membership inference attack, if somebody knows a couple pieces of knowledge about somebody in the training data, they may be able to predict that they were in the training data or not in the training data, okay? So doesn't seem that much of a problem, but if you can then do something called attribute inference, which is given some knowledge that you have about them, you can predict something new about them. When you combine those two, you predict somebody's in the original data, and you're capable of predicting something new about them, that's where you're in for major disclosure. So we developed a benchmarking tool that if anybody wants to work or just look at different synthetic data generation toolkits that are out there, ours are out there, there's about 15 others that have been developed over the last couple of years. We have a whole set of utility criteria and a set of privacy criteria that we've baked into this benchmark. The details are in this Nature Communications paper that came out last year, and the software is all up on GitHub now. And with that, I will stop and say thank you for letting me come and talk with you and ramble on this.